All right, guys, so this is going to be the second part of today's optimization lesson, okay? And we're just going to look at, I tried to give you as big of a variety of the kind of optimization questions as I could. And so we're going to look at, when you see kind of the setup of a kind of a triangle here, we're going to see one with Pythagorean Theorem, and then we're going to see one with financials, right? For those of you heading into the economics stream or something like that, okay? We're going to use calculus and economics as well, okay? So what you're going to see here is basically the question's set up in a way that initially you'll see here A naught is denoted for like the initial position of ship A, and B naught is the initial position of ship B, okay? And then after some amount of time, T, right, they've moved, right? We could call this now B final, and we could say here's, I don't know, A final, right? We want to find out basically when were the two ships closest together, at what value of T, right? Were the ships closest together, right? So basically like a minimum, right? This is an optimization question, right? And we're going to say that we've been using S for like S of T functions, right? Position relative to time, right? So we know initially, a lot of this comes down to, if you guys need a picture, you draw a picture, right? Absolutely. Kind of, if you've taken physics, you know how much a picture or free body diagram can help you, right? So we want, or initially we know that these two ships are, I'm going to try and be as spacious as I can here. Initially, we know that these two ships are 80 kilometers apart. Okay. Now, we also are told how fast each of the two ships are moving, right? So we know, if you guys remember, this is just a quick, we know that velocity is going to equal, or like speed, right? We know that speed is like, you know, distance over time. So if I was interested in, basically what they've told us here, they've told us a distance, right? So this whole question, we want to revolve around the fact, like, I want to get something like an S of T function, right? So basically like a function, a distance function with respect to time. That's what I'm interested in, right? And so in order to do that, I'm going to want to rearrange this equation to give me V times T is going to equal my distance, right? Right, because then all my units are going to match up, right? If I'm talking about like dimensional analysis, for instance, right? Any equation, I want the units on the left side to equal the right side, and so if I'm going to work in this particular question, they've told us a distance, but then they've mixed in these speeds. Well, we can work with that. It just adds a variable. That's all, right? We just don't know what time is, but that's ultimately, you know, find the distance between the two ships is at a minimum, right? So we're going to use the fact. We're going to use that, right? So we know that after some amount of time t, right, from here to here, this is how we're setting up this question. From here to here, after some amount of time t, right, we know that the ship would have traveled, ship A would have traveled 30 t, right, kilometers. Why? What is this? Well, this is the speed that they were traveling multiplied how long they moved at that speed. Speed, how long? That told me the distance in kilometers, right? That's where that comes from. Okay. Now ship B, or sorry, the remainder would then therefore obviously be by default from here to here would be 80 minus 30t. Okay, and they didn't tell us anything about the top, so we just know that the ship B is just moving away. Ship B is moving from here to here at, say, I don't know, 40 t kilometers. Right, told us what the speed was, so we just threw it in there, right, for the exact same reasoning. Okay, we want to work with this question in terms of distance, right? But the nice thing is now that we basically have a triangle here, right? We have a triangle. Not basically, we have a triangle. And it's here. I'll draw it in purple here. Okay, we have a triangle. And the thing that we're interested in is S, or S of t, right? I suppose, right? Whatever. We have a tool from way back in grade 9 to deal with triangles. It's called Pythagorean Theorem. Okay, that is the equation that we're ultimately going to derive, right? But Pythagorean Theorem tells us, so to find the hypotenuse, that's what this is. It's S squared is equal to the sum of the sides squared, right? Well, which two sides am I dealing with? Well, this one and this one. So I'm going to have 80 minus 30t squared, right, plus 40t squared. Okay, now we want to ultimately find out when these two ships were closest together, right? The distance between them, right? When they were closest. So we want to find the value of S that was the smallest value of S. Well, that sounds like we could differentiate this with respect to t, right? So we're just going to do that. We're going to find, basically, this is d of S with respect to d of t. That's what we're going to do. Okay, and then, so let's do that first, and then we'll continue the conversation. Okay, so we're going to derive S with respect to t. So I'm going to get 2S, right? But then, this is almost like there is no t here, right? We saw this earlier last week, and we're going to continue to do more of this week. There's no t here, right? So I've derived S with respect to t, but there is no t. So this was like a part of the implicit differentiation, right? So we have to treat this like a chain rule. So I bring the 2 down, right, to 2S, but because there is no t, I actually have to multiply by ds by dt. I have to state, it's like the chain rule, right? I've derived S with respect to t. Okay, the rest of it's okay because I've got t's in there, so I'm deriving this with respect to t, no problem, right? So we could say, okay, well, we've got a little bit of chain rule going on here for the first one, right? So the 2 is going to come down. We're going to get 2 times 80 minus 30t. But then I have to derive the inside. Well, that's going to be minus 30. And then I have to add 2 times 40t. I'm going to move this over here. Run out of room. Okay. And then I have to derive the inside. Well, that's times 40. Okay, there's your chain rule. There's your derivative. Okay, so if I were to clean this all up, right, I would get, let's see here. Well, I could factor out a 2 from the right. Let's do that. Okay, so we're going to this 2 here, cancel, cancel, cancel. No problem, because I would have factored it out. Okay, and so then I'm going to be left with an S. How are we going to get rid of that? Well, let's deal with this. Oh, I know what we're going to do. For a maximum, the S doesn't matter. For a max slash min, you guys know, we know, we're going to get, we set ds by dt equal to 0. Okay, so that's what we're going to do. This is going to become 0, but then the 0 is going to consume that S, right? So we'll get 0 equals, right? Or S times 0, which we know is going to be 0. I'll write that there for now, just so we don't freak out as to where the S went. Okay. Then we're going to get, well, if I were to clean up, I'm going to do some distribution here at the same time. Okay, I'm going to clean this up. So I'm going to get, what is that going to be? Negative 2400 plus 900t. That takes care of the first piece. and then plus 1600t. Yeah, plus 1600t. And I can further clean that up. The 0 consumed the s, don't worry about that. I can bring the negative 2400 over, so it becomes 2400 is equal to, that's going to be 2500t. And then t is going to equal, basically, 2400 over 2500, which is going to equal 0.96 hours. Okay. I don't think it actually explicitly did find the distance when the ships were at a minimum. Okay. Nothing too crazy. That's the time, right? Let me see here. I think what we could do here, right, after 1 p.m. I think what we could do here is take this time value and plug it into here, into the equation, right? That told us, so basically, yes. Yeah. Okay. We could take this because we could basically have S, right? S is going to equal, yeah, we could take this and plug it in right here. Never mind. Sorry, guys. Not the right one. Right there. Okay, if you wanted to find the actual distance, okay, I don't have the solution done for that, but that's what you would do. You take the time value, plug it into the t up top. It's like you'd solve for S, right? It would tell you the actual numerical value of the distance between the two ships, right? This is the time value, though. This is how long it took, okay? So if you wanted to find that, you could, right? For the purposes of time here. I don't have this done, so I don't necessarily want to type this all into there, okay? But you guys can do that if that's what's asked of you, okay? That's what would happen, okay? The important part is that you found the time at which it took place. You have an equation. This is your equation that represents the distance, okay? So if you take it, substitute the t value back in there, you'd get the actual distance, okay? That's how you would do that. All right. So we could write a little therefore statement. Therefore, the time okay, guys. So there you go. There's another application. Okay, a lot of this comes down to, can we just come up with an equation that we can derive? That's ultimately what it comes down to, right? So it's an application of your derivative, right? And a specific derivative at that. It's when the tangent, so the slope of the tangent is equal to 0, right? That's a maximum or minimum. That's the entire premise of optimization.